Example 3. Suppose f of x equals x squared divided by x minus 2. Find all the critical points of this function. So I notice here that I have one function over another function. So in order to find the first derivative here, I'm going to have to use a quotient rule. So as a reminder, when we use the quotient rule, your top function we always call f. So that's my x squared. And the bottom function is always my g, which is x minus 2. Now I need to find each of their respective derivatives. So the derivative of x squared is 2x, and the derivative of x minus 2 is 1. So now I need to plug that into the quotient rule formula. So I'm going to do f prime times g. So I have 2x times x minus 2 minus f times g prime. So x squared times 1, all divided by g squared. So I'm going to have x minus 2 squared. So my first derivative, unsimplified, looks like this. And so I know that if I want to find critical points, I want to know when this equals 0 or when it's undefined. So fractions are interesting in that they'll equal 0 as long as the numerator equals 0. If the denominator equals 0, then the function is undefined. So that means I can actually evaluate this in two pieces. I can look at when the numerator equals 0 to find when it equals 0, and I can look at when the denominator equals 0 to find when the derivative is undefined. Now I'm going to caution you, I don't recommend squaring out the denominator. It's much easier to work with if you leave it as whatever the function is squared. So first I'm going to take one step to simplify the numerator before I find any of my critical points. So multiplying the 2x through, I get 2x squared minus 4x minus x squared divided by x minus 2 squared. And then combining like terms, I have 2x squared and a minus x squared. So I get x squared minus 4x divided by x minus 2 all squared. So if I want to find critical points, I can consider when the numerator equals 0 first. So x squared minus 4x equals 0. So x squared minus 4x equals 0. These are the points when this fraction will equal 0. So I'm going to factor out an x, and that's going to leave me with x minus 4. So again, I have two things multiplied together equals 0. That means I need to set each one equal to 0 to see if there's a value that would give me 0. So the first would say x equals 0. Well, that's a value. So that's my first critical point. Now if I set x minus 4 equal to 0, I get x equals 4. That's my second critical point. So from my numerator, I have found two critical points. However, I also have to consider if my denominator equals 0, because if my denominator equals 0, my function will be undefined. So the question is, will x minus 2 squared ever equal 0? Is there a value of x that I can plug in to make this equal to 0? And the answer is yes. If x equals 2, then the denominator is going to be equal to 0 and is therefore undefined. So I have a third critical point here, which is x equals 2. So this function has three critical points: x equals 0, x equals 4, and x equals 2. So again, don't forget to check about undefined when you have denominators in your derivative. Example 4. Suppose that f of x equals x cubed times 1 minus x to the 4th. Find all the critical points of this function. All right, so here, when I look at my function, what I first notice is that I have two things multiplied together. Now, when you have two things multiplied together, that means that you're going to be doing a product rule. So for the product rule, I'm going to pick my first function to be f. So that's my x cubed. And my second function is going to be g. So 1 minus x to the 4th. Now I need to find each of their respective derivatives. The derivative of x cubed is 3x squared. Now for g prime, things are a little complicated because here I have to do a chain rule to find the derivative of g. So with my chain rule, I need to figure out what my substitution is going to be. So my z is going to be whatever is inside the parentheses, which is 1 minus x, and my dz dx is the derivative of that. So the derivative of 1 is 0, and the derivative of minus x is negative 1. So now remember, with the chain rule, you're going to have 4 times 1 minus x cubed. So we do the outside part of the derivative. That's our z part. But then we have to multiply it by dz dx. So we have to multiply that by negative 1. So now we have all the pieces we need to do the product rule to get the first derivative of this function. So we're going to get f prime times g, so 3x squared times 1 minus x to the 4th, plus f times g prime. So x cubed times 4 times 1 minus x cubed times negative 1. So we have to do some simplifying here, some rearranging. We want to try to make sense of this because, again, remember, we're going to be looking for when this equals 0. So first I'm going to do a basic rewrite. I'm just going to try to order this in a way that makes sense to me. And because I know that I'm probably going to have to factor this, I'm going to try to rewrite it in a way that'll make it easier to factor. So for each term, I'm going to try to pull the constant to the front, and then any x terms, and then any parenthesis terms. So the first term is already in that order. Constant, then x's, then the 1 minus x term. So I have 3x squared times 1 minus x to the 4th. That doesn't change. Now, the second term, I have a negative 1 and I have a 4. So I'm going to write that as minus 4. And then my x term, which is x cubed, and then my 1 minus x term. And I want to know, when does that equal 0? Well, in order to figure out when that equals 0, I'm going to have to factor this. So I'm going to be really, really careful with my algebra here. But I have two terms that I'm factoring from. And so what I need to consider first is the constants. My constants are 3 and 4. So there's not a good number that goes into both of those. So I'm not going to factor out a constant. The next thing I'm going to consider is my x terms. I want to pull out the lowest power of x. So here, that's an x squared. So from the first term, I'm left with a 3 and a 1 minus x to the 4th. From my second term, I'm left with a 4. Now remember, I only pulled out an x squared, and this was x cubed. So I still have an x, and then 1 minus x cubed. And remember, I'm trying to figure out when this all equals 0. So now I want to consider factoring out a 1 minus x term. So again, I'm going to look at the powers of 1 minus x and pull out the lowest power. The lowest power is 3. So if I pull out a 1 minus x cubed, the first term still has the 3. Now the second term had 4 of them, and I only pulled out 3 of them. So I'm left with a 3 times 1 minus x minus. Now the second term was a 1 minus x cubed, and I pulled out a 1 minus x cubed. So I'm left with a 4x. And again, I want to know when that equals 0. So finally, I need to look at what's left in my brackets here to see if I have any like terms. So the first terms stay the same. And now inside the brackets, I get 3 times 1, which is 3, and 3 times negative x. So that's going to give me a negative 3x. But then I still have the minus 4x. So negative 3x minus 4x is going to give me minus 7x. So now my derivative is fully factored and fully simplified as much as I can. So again, I have 3 things multiplied together. I need to set each one equal to 0 to see what my critical points are going to be. So the first term multiplied in is x squared. If x squared equals 0, that tells me that x equals 0. So that's my first critical point. Now here, if 1 minus x cubed equals 0, I can see that x equals 1 would make that whole parenthesis 0. So x equals 1 is my second critical point. And then finally, I set 3 minus 7x equal to 0. If I solve for x, I can bring the 7x over. So 3 equals 7x. So x equals 3/7 is my third critical point. So here, my critical points are x equals 0, x equals 1, and x equals 3/7. Here, the algebra is a bit tricky. As long as you're really careful about your factoring, however, you should be able to get to your critical points. Let's try another. Example 5. Suppose f prime of x is given in the graph below. Use the graph to determine the critical points of f of x on the interval given, -2 to 8. So here, what's really important is that we understand what we're looking at. This is a graph of the first derivative. So we have to remember how we find critical points. Critical points are going to be when the first derivative equals 0 or when the first derivative is undefined. There's nowhere on this graph that's undefined, and so we're looking for where the first derivative equals 0. The first derivative of a graph of the first derivative is going to equal 0 whenever we cross through the axis. So here, here, and here. So these are the points where the first derivative equals 0. And these are the points, therefore, where the original function, f of x, is going to have critical points. So there's 3 of them. The first one is at x equals 0. The second one is at x equals approximately 3.1. And the third one is going to be approximately, let's say, 6.3. I suspect, and this is just a guess, but I suspect that this is at pi and this is at 2 pi. But I'm estimating close enough. Pi is 3.1, so 3.1 or pi would be fine here. But the idea is that we're looking for the place where this first derivative graph crosses through the axis, because that's when the first derivative will equal 0. Let's try another example. Example 6. Suppose that f of x and f prime of x are continuous functions that are differentiable. Given the table of values for f prime of x, determine the most likely places that f of x would have critical points. So similar to the last problem, we have information about the first derivative here, and that's really important to make sure you understand what kind of information you have. So here, again, to find critical points, I want to know when the first derivative equals 0. So an initial scan of my table indicates that my first derivative is going to equal 0 when x equals 6. So x equals 6 is my first critical point of f of x, of the original function. However, there's another sneaky one kind of hidden in here. So we see here at the end of the table, between x equals 10 and x equals 12, the derivative changes signs. It goes from +2 to -1. In order for a function that is continuous to change signs from positive to negative, it has to go through 0, which means that somewhere between 10 and 12, there's another spot where my first derivative equals 0. It's not as precise as x equals 6, so I'm going to say over here, between x equals 10 and x equals 12. So it could happen at 10.1, it could happen at 11, it could happen at 11.4, but I know that somewhere between 10 and 12, I had to cross through the axis to change signs, so there has to be a critical point in there. So this table has 2 critical points, one at x equals 6 and one between 10 and 12. Now these are the most likely places. Of course, we don't know what's happening between the values, between 0 and 2, between 2 and 4. So this analysis is based on the values we have. Let's look at another example. Example 7. Suppose that f of x equals ax squared plus bx minus c, where a, b, and c are non-zero constants. Find the critical points of this function. So again, my independent variable here is x. Everything else is a number. So if I want to talk about critical points, again, I'm interested in where my first derivative is 0 or undefined. So here, my first derivative of this function, the first term, ax squared, the 2 is going to come down to multiply the a from our constant multiple rule, and I get 2ax to the 1 plus the derivative of bx is just b, because again, that's the rule mx. The derivative is just the constant in front of x. And the derivative of c is 0 because c is a constant. So I want to know, when does that equal 0 or when is that undefined? X to the 1 is not going to be undefined anywhere. It's defined for all values. And so therefore, I just have to consider when this will equal 0. So here, that means I want to solve for x, because again, x is my variable. So first, I'm going to subtract the b over to the right. And now I'm going to divide both sides by 2a. So I get x equals negative b divided by 2a. So that is going to be where my critical point is, which means I can vary a and b for different polynomials, and I'll always know where the critical point is because I can plug the a and the b into this formula. It's a nice way to find a general place that we're going to have a critical point. And it's something, again, that we can do because we know about derivatives and because now we know about critical points. What's really important, however, is that you remember what letter represents your independent variable. That's what you're going to be solving for. Everything else needs to go to the other side of the equation when we're solving for 0. Let's look at one more example. Example 8. Suppose that f of x equals ax e to the negative bx. Find the critical point of this function. So again, x here is going to be my independent variable, which means that a and b are constants. And so what I want to do again is find the first derivative of this function and see where it equals 0 or is undefined. Now, in order to get to the first derivative of this particular function, I notice that I have two things multiplied together, ax and e to the negative bx. Those both have the variable of x in them, so I'm going to have to do a product rule. Separating out these functions, my f is going to be ax, and my g is going to be e to the negative bx. Now I need to find each of their respective derivatives. The derivative of ax is just a, and the derivative of e to the negative bx needs a chain rule. Remember, with e's, your z is the power of e, so negative bx, dz dx, the derivative of that is negative b. So with e chain rules, we get the same thing back, e to the negative bx times dz dx, negative b. So my first derivative here, we're going to do f prime times g. So I have a e to the negative bx plus f times g prime. So ax e to the negative bx times negative b. So again, I'm going to do a little simplifying before I start factoring anything. So I'm going to write my function by constants first, then any x terms, and then the e term, just so that both terms are in the same order. So my first function is already in this form. I have my constant a, there's no x terms, and then my e term, e to the negative bx. The second term, I have this negative here from the b, so I'm going to make that minus. Now my constants are a and b, so minus ab, then x, and then my e term, e to the negative bx. You don't have to rewrite it this way. I just find it helpful for me. So now I want to know, when does that equal 0? So again, I'm going to look at what my terms have in common. So both terms have an a, and both terms have an e to the negative bx. So those are going to be the things that I'm going to factor out. So ae to the negative bx. So if I have ae to the negative bx in the first term, and I factored out the entire thing, That leaves me with a 1 placeholder. If you factor something out and you factored out the entire term, you need to leave a 1 there, because if you were to multiply it back in, then it needs to multiply 1 so it can show up there again. Now from the second term, I took out the a and the e term, which leaves me with bx. Now I have 3 things multiplied together equals 0. Now a is a constant. And a, when we have constants, are generally non-zero constants. So my a is not going to equal 0. E to the negative bx. Hopefully you remember from algebra what exponential functions look like, but e to the negative bx will never equal 0. There's nothing that you can plug into that function that will make it equal 0. Therefore, the only time I can get a 0 is from that last parenthesis here, 1 minus bx. So if I set that equal to 0, and remember, x is my independent variable, so that's what I'm trying to solve for. I have 1 equals bx if I bring that term to the right. So that tells me that x has to be equal to 1 over b. So even though I don't know what a and b are, I know that the critical point is at 1 over b, because I solved this in general with constants as placeholders. So this function has one critical point, and it happens at x equals 1 over b.